There's something about my voice that just puts people to sleep, October included. And I've literally had people, students and non-students, say that they will turn on my videos to fall asleep. So that's not the best for a classroom situation, but here we are. Let's do some more examples on linear applications. If you want, if you're feeling bold, you can try this one now. Try this problem, pause the video, and see how you do. Otherwise, let's go through it together. I'm not going to use the official step-by-step method again, but I'm going to go through them with basically the same idea. So Jamal is choosing between two moving companies. This data came from 2010. The first, U-Haul, is charging an upfront fee of $20 and then it's charging an extra 59 cents every mile. Right off the bat, here's what I'm seeing. $20, that's like a fixed cost. That's looking like a B value. 59 cents a mile, that's looking like some kind of slope, right? It's a rate of change. Also, I'm noticing that this is in dollars and this is in cents. That's going to be a problem. In the first situation, we went through all the information and then started looking at things. But sometimes it can be more manageable. If you don't want to get overwhelmed, sometimes it can be more manageable to stop and identify things as you're kind of going along and making notes to yourself. The second, budget, charges an upfront fee of $16. Well, that's another B value. Maybe we'll call this one B1 and this one B2. And then we have got another slope, 63 cents per mile. Sounds like another slope. Maybe slope 2, I don't know, and slope 1. When will U-Haul be the better choice for Jamal? Okay, so we've got a bunch of quantities. Our first step in the last one was giving variables for these quantities. Let's start with that. What quantities does Jamal care about? Well, he's probably going to care about how much money he's got to pay, right? So let's say that we care about the cost. Let's call that C for Jamal. What does the cost depend on? The cost depends on how many miles he's driving for his move. So we can say that's based, again, this is going to be in dollars. Units are important. The cost C is based on or depends on miles driven. You can have that be M. All right. A lot of different options here. So these are the two quantities that are interacting with each other. What are we trying to find? When will U-Haul be the better choice for Jamal? Oh, so there's two different costs, right? There's the cost of U-Haul and there's the cost of budget. So maybe we say C1 is the cost for U-Haul. And maybe we'll say the budget cost. You can call that C2 also in dollars. And it has the same input variable, how many miles he's driving. In reality, that would be like a little different. M would be a little bit different because you do have to, like, at least when I do it, you do have to return it. You're driving the return thing. So unless U-Haul and budget are in the same parking lot, they'd be different. Let's say they're in the same parking lot, okay? Same number of miles that we're driving. All right, so when will U-Haul be the better choice? How can we write that with math? When will U-Haul be the better choice? U-Haul is C1. U-Haul's the better choice. The cost of U-Haul is better for Jamal when that cost is smaller than budget. So when is the first cost smaller than the second cost is how we can translate this question. This is what we want to find. Cost of U-Haul, we said that's C1. Cost of budget, C2. The question is saying, when is U-Haul better? Well, that's going to be when the first cost of U-Haul is less than the cost of budget. Okay? And we can find that in a couple different ways. In a previous section, I think it was 1.5, we talked about finding when is one function smaller than the other. To do that, we find their point of intersection. Okay? So to find when one's smaller, we're going to first start and say, well, when are they equal? And then one will be smaller on one side, and maybe the same one or maybe a different one will be smaller on the other side. Okay. So let's find, to do this, this is like our pathway. Find this. First, let's find when they're equal. You actually can just solve this inequality if you want, but we haven't really talked much about solving inequalities, so I'm going to do it in the way that the book recommends for where we're at. But again, there's a lot of different ways of solving these problems. Okay, well, in order to find when these things are the same, we have to know what these things are. What is C1? What is C2? And then if we can find them, we can find their point of intersection. The intersection of those two lines, that is 1.5. Okay, well, the cost for the first one, U-Haul, is a flat fee of 20 bucks and then 59 cents a mile. We can write that as a line, right? Y equals B plus MX. Flat cost of $20. And this is where it's really important that C1 is in dollars. So if a flat fee is $20, B is just directly B1, or B is just directly 20. But it's 59 cents every mile. Remember that 59 cents, we need all the units to be the same. So 59 cents is $0.59 for every mile. And again, we think of it as Y equals B plus MX, but in reality, our variables have different names. We don't have Y, we have C1. We don't have X, our input is M, the number of miles. Okay, so there we go. We have an equation. Let's do a quick gut check to make sure that this equation makes sense. If we don't drive any miles, if M is 0, what's our cost? 20 bucks. That sounds right. If we drive 10 miles, what's our cost? 20 bucks, and then an extra $5.90 is what the equation says. And that matches up with what we think it should be as well. $25.90 for 10 miles. Okay, so it looks like we got this right. And then we can do the C2, the budget charges, the same way. All right, we said that B value is 16, and it was charging 63 cents a mile. We have our two equations. We can find out their point of intersection by graphing or by setting them equal to each other. So C1 equals C2. Well, we know C1 is 20 plus 0.59 miles. That is exactly what C1 is. Right? This is C1. And C2 is exactly 16 plus 0.63 m. So they're equal when what they're equal to is equal to. That made no sense, right? This is C1 right here. This is C2 right here. So C1 and C2 are the same when their right-hand sides are the same. So those mean the same thing. And now we just solve for M. So again, you can do things however you want. I'm going to subtract over the 0.59 m because I like positive variables. But you don't have to. That'll give us 20 is equal to 16 plus 0.04 m. Subtract 16 from both sides. And you'll get that 4 is equal to 0.04 m. Divide both sides by 0.04. You could also multiply both sides by 25. It would be the same thing. And you should get that m is 100. That's not our answer, though. 100 miles driven is when these costs are going to be equal. We could say the costs are equal after 100 miles. But when is U-Haul going to be better? There's a couple of ways of finding that. Right? U-Haul has cheaper per mile. Okay, so that means that, right, if U-Haul is cheaper for every mile, then U-Haul is going to be cheaper after this, right? If this is when they're equal and U-Haul is cheaper with every mile, then U-Haul is going to be cheaper after this, is one way you could do that. The other is you could just check. What are the costs after 101 miles? What are the costs after 110 miles? Check which one's smaller. The U-Haul is better for Jamal after 100 miles. And again, if we really want to gut check our answer, let's see what the costs are for 110 miles. We're going to visualize this with a graph. We said C1 was something. 20 plus 0.59 M. We said C2 was 16 plus 0.63 M. Let's look at these graphs. And again, you might say, there aren't any graphs, Jason. What's the deal? Remember, hit over here, put inputs and outputs that make sense. So we said their break even is at 100 miles. And if we want to label this, we could label this M. Our horizontal axis is M, the number of miles. So let's look between, I don't know, 0 and 200 miles. The y-axis is the cost. We're not going to have negative costs. We could start with 0. And again, we could label this C. And I don't know, we could just guess some costs that make sense. And you can see that for most of the time, they look pretty similar, right? Where do they break even? At 100 miles, just like we said. Which one's cheaper? And be careful, better doesn't mean bigger, no matter what you've been told. Better for Jamal is cheaper. So notice that to the left, orange is cheaper. To the right, blue is cheaper. Maybe let's zoom in a little bit on the x-axis. Let's look like from 80 to 120. And on the output axis, the cost axis, maybe let's look at from like 60 to like 100. That did not make it clearer, Jason. That was terrible. Okay. I'm sorry. Let's zoom out in the x-axis. It's still hard to see. But notice that blue is cheaper. U-Haul is cheaper to the right, which is what we thought. Okay, so that's one way of checking our answers. Let me know if you have any more questions. Let's make sure we answered the question. Good. We're good to go. Oh, there's another one. Great. Let's do the other example together. Again, feel free to pause the video and try it now. And then we can talk through it afterwards. So we have some company and their revenue has been growing linearly. In 2012, the revenue was $1.45 million. In 2015, the revenue was $1.81 million. If this trend continues, predict the revenue in 2020. Okay, so if it's growing linearly, we know we're going to look at something in this form. What are our variables? Well, we're definitely looking at revenue. Let's say revenue, and be careful. Here, let's talk about revenue in millions of dollars. It's going to save us from drawing a bunch of zeros. And then what's revenue related to? Time. So let's say we can have it be T years after the start. If you want smaller numbers, this is the best way of doing it. Or you could just have in year Y and then plug in 2012 as your input year. You're going to be plugging in bigger numbers, but there's nothing wrong with that. Okay, and you'll get the same answer. So let's update this. It's not going to be Y equals B plus MX anymore, right? Our output is the revenue. Our input is time. So like that's a good place to start, but make sure to always replace it with your variables. Okay, so now we can look at some points and find some slopes. Because we do know the starting value, right? We know that the revenue, we know our B value. The starting value in 2012 was 1.45 million. But we don't know the slope. We know in 3 years it's changed by $0.36 million. We could use that to find the slope, but let's find it in a different way. Right? 2012, revenue was 1.45 million. That's the 0, 1.45. 0 years after 2012. We know in 2015, the revenue was 1.81 million. So that's 3 years after the start, 1.81. We can use these 2 points to find the slope. Our slope is going to be the second output minus the first output divided by the second input minus the first input. Just like I said, this is going to give us 0.36 over 3. Our slope is 0.12. It's growing by $120,000 every year, or $0.12 million. And I said that putting revenue like this is nice because we don't have to write a bunch of zeros, but we do have to write decimals now. So I don't know, pick your poison. If you had revenues in thousands of dollars, you might have to convert, but then you wouldn't have as many zeros and you wouldn't have any decimals if you did thousands of dollars. But here we go. This is our revenue function. Revenue function in that framework, that step-by-step framework in the first video, steps 1 through 8. Finding the revenue function is our pathway to answering the question. We wanted to know what the revenue is. Well, to get there, we need to model the revenue. So 2020, that's 8 years after our start. This t is going to be 8. And again, if we wanted to, and I will do it this way to get some practice, writing this in function notation, revenue is a function of t. We could write r of t. This is the same way that we write f of x. Just our function now is revenue. Our input is now t. So r of t could work. So we're curious about what is the revenue. What is the revenue when we're inputting 8? This is not multiplication. This is function notation. This says the revenue after 8 years. And it's just one variable. That's going to be 1.45 plus 0.12, plugging in 8, 0.96. You can type this into a calculator. 0.45 plus 0.12 times 8, 2.41. 0.41, again, millions of dollars. That's going to be our predicted revenue in 2020. And again, let's gut check to see whether this kind of makes sense. And once we found our formula, we could have also gut checked that one. All right, if we did plug in 3, if we did find the revenue 3 years later in 2015, hopefully we get 1.81 million. Our revenue is growing by the same every year. So after 3 years, it went up 0.36. So it should keep going up by about that much every 3 years. This sounds ballpark, sure. Our answer kind of makes sense. When will the revenue be 3 million? So how do we phrase that in math? When is the revenue equal to 3 million? Now I'm giving you an output and I want you to find the input. In A, I gave you the input of time and I wanted the output revenue. Here, I give you the output revenue and I want the input of time. So again, we know the revenue. We found the revenue after 8 years was $2.41 million. So if it's growing every year, our answer should be after 2020, right? If after 8 years it was 2.41 million, we're curious, when is it going to be 3 million? Well, it should be some future time because we're growing every year. So the revenue is this. When is this equal to 3? Well, it's equal to 3 when it's equal to 3. Right? This right-hand side, that's the revenue function. The left-hand side is 3. When is it equal to 3? When this happens. Solve for t. Subtract 1.45 from each side. I'm going to give you 1.55 over here is equal to 0.12t. And then we can just divide both sides by 0.12 to get t by itself. Not doing that in my head. 1.55 divided by 0.12. That's going to be 12.916 with the 6 repeating. That's about 13. Okay? Approximately 13. So about 13 years later, the company's revenue will be about 3 million. What was 13 years later? Years after 2012. So 13 years after 2012, so around 2025 is the answer to the question. And again, the problem-solving strategy says to answer in complete sentences where it makes sense. But here, right, if the question is, when will the revenue reach $3 million? An answer of around 2025 really makes sense. That directly answers the question. I don't think you necessarily, for my class, need to rephrase the question when putting the answer. As long as your boxed answer is the direct answer to the question that was asked, it makes sense. So if we just boxed 13, that wouldn't make any sense. When's the revenue going to be $3 million, Bob? 13. That doesn't make sense. But when is the revenue going to be $3 million, Bob? Around 2025. That makes sense, okay? Have a good one. Let me know if you have questions. I know these videos are long, but I really want to give you guys enough examples. So if these things are feeling really easy, you can skip through the videos. If they're feeling hard, you can slow down, rewind, pause, and spend some more time with it. I'm trying to give you guys the options, giving y'all the power. So with great power, something responsibility. I don't know. Bye-bye.